Okay, let's start. Good morning. So this week we're going to be looking into what is called linear subspaces. So I guess the level of abstraction is going to sort of increase slightly. But before that, I wanted to spend one more class on this inverse operation, finding multiplicative inverse of a matrix, and do a couple of numerical examples, especially in higher dimensions, and sort of look into this row reduction a little bit more. Okay, so here I wrote, again, sort of like the cheat sheet. If I have, first of all, a 2x2 matrix A, B, C, D, then I have two situations. I look at this number, AD minus BC. It's a function, if you want, of the entries of A. Either that, whatever that value is, it is 0, in which case A inverse does not exist. Or else, right, that's the only other option, this number AD minus BC is not equal to 0, in which case that's the formula for the inverse. Okay? And the trick to remember this is to say, okay, I'm just going to flip the diagonal entries. So AD became DA, and then I'm going to put minuses in front of the off-diagonal entries. Okay? Now, people usually don't write it like this. They just write the second box with the understanding that because here I have this number in the denominator, if it is 0, that doesn't make sense, obviously. So they just like compress all this box, all this board to this box. So that's 2x2. In higher dimensions, so the inverse of an n by n matrix, we have an algorithm. It's basically the algorithm that I went through last week to discover this formula. Okay? And this algorithm tells you at the same time if A is invertible, and if it is, it computes A inverse. Okay? So for now, this is the method that we're looking into, but later on, after the first midterm, we're going to really separate this stage from this stage. So the question of whether or not the matrix is invertible is one thing, and the question of whether or not what the inverse is another thing. So it's good to separate the concerns, as what they would say in computer science, for instance. And so later on, we're going to really learn the analog of this value, AD minus BC, which we call determinant, for higher dimensional matrices. For now, these two concerns, whether or not a matrix is invertible and what the inverse is if the inverse exists, are joined. And the algorithm is this. I want to solve AB equals I is identity matrix, for B. Okay? And all of these are square matrices. Maybe I should write it like that. So N, 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 N. I want to solve for this. So what I can do is I can transform this into an augmented matrix. Now I'm augmenting not only a vector, but a matrix to a matrix. Okay, so this is a matrix, this is a matrix. So now this new augmented matrix has n rows and 2n columns. So I might as well write it like this, n to n. Then I can row reduce, as usual, this augmented matrix to reduced echelon form. Okay? I still don't know if A is invertible, but I can still do row reduction. If I can row reduce this augmented matrix to I and then some other matrix, then that means that whatever is duplicated on this right-hand side is going to be the inverse of A. If not, that is to say, if the reduced echelon form is of a different type here, then that means that the inverse does not exist. Okay? I should also mention here, I wrote that most matrices are invertible. There's a way to make this more rigorous, but for now, let's think of it this way. Let's just look at 2x2 matrices. Whether or not this matrix ABCD is invertible depends on the value of AD minus BC. Now, what is the likelihood of this expression being equal to 0? Right? So even if it were 0, if one of the entries were a little different, then it is likely that it's not going to stay 0. It's going to change. So that's why what people say is that this is the generic case, and that is the non-generic case. So generic case or the typical case. And then this is the non-generic case. Which means that even if, so in this case, even if you're in this case, it's not a super bad idea to just assume that before starting this algorithm that the matrix is invertible, okay? Because it being non-invertible would be a surprising thing in a sense, okay? Okay, so examples. Last week we did a bunch of examples of matrices that are invertible. Here's an example of a matrix that is not invertible. 2, 3, minus 4, minus 6. Now, immediately you should say, oh, there should be something weird going on here, because the second column is minus 2 times the first column, right? So there is something weird going on here. But let's approach this from different perspectives. So first of all, I can compute the determinant, okay? And I'm just going to write it like this. DET, so determinant of A, okay, is AD minus BC. So this is minus 12 and then minus 12, which is 0. Okay? According to that, or according to this board, this is not invertible. Okay, so this is one way of doing this. It's rather straightforward. But let's also use this algorithm that I mentioned to really understand how it gets stuck at this third stage. Okay, using the algorithm. So when I augment my matrix, it turns into this. And then 1, 0, 0, 1. Okay? So now what I can do is this. I can take, for instance, let me do this step by step. Let me divide the first row by 2. So row 1 replaced by 1 over 2 times row 1. I'm going to do this step by step. 1 minus 2, 1 over 2, 0. And then the second row stays the same. Then let me do the same thing, or the corresponding thing for the second row. Let me replace row 2 by 1 over 3 times row 2. So now the row 1 is the same, but then this one turns into 1 minus 2, 0, 1 over 3. Now next, what I can do is, for instance, I can take the first row and subtract it from the second row to get rid of these two entries. So row 2 replaced by row 2 minus row 1. This is sort of like a review of row reduction as well. And so once I do this, I get this. 1 minus 2, 1 over 2, 0. And then this is 0, 0. This is minus 1 over 2, and then 1 over 3. Now note that this is in reduced echelon form. Well, it is not quite in reduced echelon form because of this. What matters is that on this left side, I don't see the identity. You see, I don't see a 1 here, and I cannot see a 1 there. So this is as far as you can go. Let me write it here. This is not identity I, which means that it is not invertible, this matrix. So on the right-hand side, I did generate some numbers, but that doesn't matter. If you can't get identity on the left side, all bets are off. Not invertible. let me also add this terminology that is also fairly common. People also use the word singular for not invertible. Okay, that's another phrase that is very common, aka singular. And then they call invertible matrices non-singular, of course. Okay? Any questions about these two? So this is a fast way of doing this. This is a slightly longer way of doing this that scales at this stage, scales the higher dimensions. Let's think further. Let's think of this geometrically. What is happening here? Now recall, so the inverse of A would take outputs of A and turn them into inputs of A, right? It would just operate in the other direction. So say there is a matrix B such that, let me say, B times A equals I. Okay? So if I were to, B times A times xy would be I times xy, which is xy. And this I know to be B times, so this is 2x minus 4y is the first entry, and then the second entry is 3x minus 6y. It's a 2 by 2 matrix. Okay? And turns it back into xy. Now here's the picture. Let's use x and y for the inputs of A, and for the outputs, let's use u and v. Now note that I can write this as a certain linear combination of 2, 3, and minus 4, minus 6. Right? I can split it. But of course, because this is minus 2 times this, I can as well do the following. So this is x minus 2y. This is a scalar multiplied by 2, 3. Okay? This is a scalar. Note that if I were to use this scalar to scale this vector, I would get this vector. This tells me that no matter what input I put in, right? No matter what input I put in, eventually the output will be a constant multiple of 2, 3. So 1, 2, 3, 1, 2, 3. 2, 3 is here. So A takes this whole plane, no matter what the output, no matter what the input is, and turns it into some vector here. Now, initially we said that the output space is two-dimensional, but when you really think about it, you can't really get every single thing in this output space. You can only get those outputs that are on this line. If this is the case, then note that geometrically speaking, I shouldn't be able to get back any single input whatsoever, because I want my vector to take whatever here and bring it back to this space. Certainly there is no such matrix, because you squished your space. Okay? Can't exist. So let me write it like this. Can't exist because output space is 1D. it's one-dimensional. Okay, it is squished. Okay, this is yet another way of thinking of what is happening. Okay, any questions about this? Okay, let's do another example with now 3 by 3 matrices. Okay. This is the example that I want to do. Let's look at this matrix. Now, later on, after the first midterm, we're going to learn how to compute the determinant of this 3 by 3 matrix. It's, again, a formula. It's slightly more complicated than the one that we have over there. But still, there's a formula. But at this stage, we don't have access to this formula. Okay? So what we're going to do is to use the algorithm. Okay? So step 1 is to augment this with the identity matrix over here. So AI is this: 0, 1, 2, 1, 0, 3, 4, minus 3, 8 is A. And then I have 1, 0, 0, 0, 1, 0, and then 0, 0, 1. Okay. So let's start row reducing. What I can do is I can take the second row, subtract 4 times it from the third row. This is just week 1 still, right? I'm not doing anything new. Row 3 replaced by row 3. Actually, let me use a different color for that. Row 3 is replaced by row 3 minus 4 times row 2. I didn't do anything with row 1, so this turns into this: 0, 1, 2, 1, 0, 0. Second row stays the same: 1, 0, 3, 0, 1, 0. The third row changes. This is now a 0. This has to stay the same because this is 0. So now I need to subtract 12 from 8, which is minus 4. Minus 4 here again. This is 0. It stays as 0, and this is 1. Okay. So what can I do now? I can take this multiplied by 3 and add it to this to get rid of this entry. Okay. So let me write it here, like so. I want to take the first row and add 3 times it to the third row, right? Let me put these in boxes. Say again? In the third row, when the second minus 4 went to the right. I missed it again, sorry.
Because it's R3 minus 4, R2, but the minus 4 is...
Oh, yeah, I used this guy, right? Sorry, thank you. Thank you. Thanks. Okay, is this okay now?
I think so.
Yeah, okay, good. Okay, so now I do this, and the first and second rows are going to stay the same. The third row is changing. This becomes 0. So now from this, I need to get 6 minus 4, which is now 2. This, it becomes now 3. This stays the same. This stays the same. Okay. Next stage, what I can do is I can divide the third row by 2 to simplify this and get a 1 here. This might be boring at this stage, but I think it's good review. Okay. So if I do this, I get this 0, 1, 2, 1, 0, 0, 1, 0, 3, 0, 1, 0. Then here I have 0, 0, 1, 3 over 2 minus 2, 1 over 2. Okay. Let's continue. I can subtract twice the third row from the first row to get rid of this. Now, recall that typically you can just combine a couple of these operations. I'm doing this step by step for a reason. So now, next stage is row 1 replaced by row 1 minus 2 row 3. Okay, let me just write the second and third rows first, and then I can modify the first one. So the first one is being modified now, 0, 1, and then this becomes 0. If I subtract minus 3 from 1, I get minus 2 here. If I subtract minus 2 times, or if I multiply this by minus 2, I get 4. So this is going to be a 4. And this should be a 1 over 2, of course. And it's a minus 2. OK? Next stage. Again, I can take the third row, subtract from it, from the second row 3 times the third row. Let me do it here. This? Oh, that's minus 1, I guess. Oh, because, wait, why?
Because isn't negative 2 times 1 half just 1? Or negative 1, I mean, sorry.
This is correct, no? OK. Thank you. 0, 1, 0, minus 2, 4, minus 1. Second row is going to change. Third row is 0, 0, 1, and then 3 over 2 minus 2, 1 over 2. Now here, I should get this, 1, 0, 0. Now if I multiply this by 3, I get 9 over 2. So that's minus 9 over 2. If I multiply this by minus 3, I get 6 plus 1, 7. If I multiply this by minus 3, I get minus 3 over 2. So I get here minus 3 over 2. And then the final stage is to shuffle these rows. Let me do this 2 in, I guess all I need to do is to shuffle these 2. OK, straightforward. Row 1, replaced by row 2 and vice versa. To get this, 1, 0, 0, minus 9 over 2, 7, minus 3 over 2 is the first row now. Second row is 0, 1, 0, minus 2, 4, minus 1, and then 0, 0, 1, 3 over 2, minus 2, 1 over 2. Now you see, here we were able to get the identity matrix. This is the 3 by 3 identity matrix. which means that this matrix over here is the inverse. Okay? Any questions about this? This should be all straightforward at this stage. Let me just check that I've did this correctly. It seems correct according to the book. But if you're out there without any means to verify this, what you can do is you can multiply, of course. And let's also multiply these matrices as a review as well. So that means that if I were to take A, that matrix, multiply it by this matrix, I should get this matrix. Okay, that's one way of checking it. And also let me note here, you see in the case of 2 by 2, each of these entries were functions of the entries of A. And A had 4 entries, which means that each of these entries were dependent on 4 variables. But now in this case, each of these entries depend on each of the entries of A, which means that all of these are functions of 9 different variables. Now it's not as straightforward what the formula should be, you see. At least at this stage. So check. A times A inverse is this. 0, 1, 2, 1, 0, 3, and 4 minus 3, 8 is A. And then A inverse is, it's harder to memorize, minus 9 over 2, 7, it's gone, minus 3 over 2. So first row, minus 2, 4, minus 1. And then the third one is 3 over 2, minus 2, 1 over 2. Minus 2, 1 over 2. Okay. Recall the rule. The rule was to split the leftmost matrix into rows and split the rightmost matrix into columns. Okay. So now at the end, you see I'm going to get a 3 by 3 matrix, of course. Zero times minus 9 over 2 is 0. Minus 2 plus 3 is 1. It's 0, 4, minus 4, 0. Goes away. Minus 1 plus 1, 0. This is a stunt, of course. I know that it's going to end up being the identity, but anyway. So this is minus 9 over 2, 0, plus 9 over 2, 0. 7, 0, minus 6, 1. Minus 3 over 2, plus 3 over 2, 0. Because mentally, right, when I see a 0, I know that the corresponding entry is not going to contribute anything. So I can just fast forward it a little bit. 7, wait, sorry, this one. 4 times minus 9 over 2 is 2 times minus 9, which is minus 18, plus 6, minus 12, plus 12, 0. 28 minus 12 is 16, minus 16 is 0. And then finally, minus 6 plus 3 plus 4 is 1. Okay? So it works. Technically speaking, you should sort of look at this as well, but I'm just going to leave this multiplication to you. Okay? Any questions about these? This is how we can invert matrices. Questions? You have a question? Yeah.
So when the first example where you sort of like elaborated on why it wasn't invertible rather than just using this idea.
Yes.
The whole point that you made was because you can think of the matrix as like the product of x minus 2y times some ratio. The idea is that you're never going to be able to access your entire x and y space because it's always going to be multiplied by some ratio.
Yes.
That's the point.
Yes. Not initially, but if you first apply A, then you won't be able to access it any point here if you wanted to revert the operation procedure. So let's say that you have something, okay, you have some input space, and you have a machine that transforms your input space into some other thing, okay? So your inputs are now outputs, but you're like, oh, I want to control Z. It doesn't work because it's gone. You sort of like flush the memory somehow. Okay, so it's gone. You need to do it from the beginning again. So you need to apply A again if you really want to start from the beginning. It's like you start your program from the beginning. Okay. Any other questions? Okay, let's continue. For instance, here's another example using this idea. Yeah. Nice. Today's class is somewhat leisurely because I wanted to make sure that all the stuff that we've been discussing so far are sort of coming together properly. Starting from tomorrow, things are going to ramp up again. So.
Is this a class where we have like a review day before midterms and stuff, or is it not like that?
I mean, it turned out to be that way, but I wasn't actually intending it to be. I'm going to switch the lenses here in a second, but still. No, it's just that this the linear subspaces stuff that we're going to discuss starting from tomorrow, as far as I can see, I can imagine, it is somewhat more conceptually taxing. And it's just that before switching over to that, I just wanted to make sure all the computation stuff is all good and you're comfortable with all these operations and stuff. You see, I'm still using week 1 material. So. Solve, so let me write it like this. AX equals B, where A is, as in this case. So let's say it is 0, 1, 2. 1, 0, 3, 4, minus 3, 8. And let's say B is 1, 2, 3. 2, 4, 6. Okay. Now, you can again use the operations, the row reduction and stuff, and start from the beginning, right? So augment B to A and do row reduction and stuff. But we've done this already, in a sense. And further, I also have an inverse, multiplicative inverse. So what I can say immediately that if this is the case, much like canceling out number multiplication, right? You can send a number to the other side as a division. You can do the same thing with matrices insofar as the inverse exists. Okay? So now this is the identity matrix, and I know that X, the solution, is this. So you see, the inverse of a matrix is also sort of convenient in the sense of it provides a compact notation. It turns out that in terms of, so for the purposes of applications, it's not really a very good idea to invert a matrix due to complexity reasons, which I hope to discuss at some point. But for now, let's take that for granted. When it comes to applications, you really don't want to invert matrices. In fact, there are a lot of pages on the internet that says don't invert the matrix. Do something else. There are other things. And I'm just trying to sort of motivate all that stuff. Eventually, I hope to cover those as well. But for now, let's just keep in mind that inverting matrices is not very practical, but for the purposes of abstract calculations, it's fine. And so all I need to do is to compute this multiplication, okay? Because I've computed the inverse. It's over there. So I can just take this vector and apply this matrix to this vector to get the solution. So A inverse is over there, minus 9 over 2, 7, minus 3 over 2, and then minus 2, 4, minus 1, and then 3 over 2, minus 2, 1 over 2. And B is 2, 4, 6. So this is now minus 9 plus 28, minus 9 again in the first row. The second row is minus 4 plus 16 minus 4. The third row is 3 minus 8 plus 3. So 2 by 2, 3 by 1, sorry. So this says 28 minus 18 is 10. 16 minus 8 is 8. And 6 minus 8 is minus 2. So that's another way of solving this. Okay? If someone told you what the inverse of a matrix is, you could just apply it like this, and instead of do a row reduction like this, which takes slightly longer perhaps to write, you can just multiply. Okay? Any questions about this? So that means that if you know the inverse of a matrix, you can use it to solve a system. In the problem set, in problem set 3, that is due this Friday, there's a problem like this. It asks you to invert a matrix and use the inverse of the matrix to find the solution to a certain linear system. This is what the problem is really asking you to do. Okay? So this is like the third part of the same problem. In the first part, it's asking you to compute the inverse and so on. Any questions? Okay. So now let's change our lens a little bit more. Recall that I've been saying that linear algebra is somewhat self-referential. A lot of the things that you do in linear algebra to solve problems are linear algebraic operations. And this really applies to these row operations as well. Okay? And this is related to the notion of the so-called elementary matrices. So this is, let me say, example star. Let's continue from this example star. The only other context in which we saw the word elementary in this class, in a technical sense, was in the context of elementary row operations. And the main idea here is that to each elementary row operation, there corresponds a certain matrix. And really, doing this row operation can be formulated in terms of matrix multiplication. So the idea is that, so these correspond to elementary row operations. And here's how. Let's take the first operation, row 3 replaced by row 3 minus 4 times row 2. And recall here, this notation really means these are the old rows, and this is the new one, right? So these are this is the input, and this is the output. Just to be slightly more clear, let me just use the notation R3 prime, the new row 3. Okay? So now, instead of this abbreviated notation, what I can write is the following. New row 1, new row 2, new row 3 equals, I didn't do anything to row 1, so it stays the same, even though I call it the new. New row 2 is the same thing as the old row 2, and then the new row 3 is really this, minus 4 times R2 plus R3. Now you see I can write this as a certain 3 by 3 matrix applied to the vector R1, R2, R3. This is 1, 0, 0, 0, 1, 0. You see, I didn't do anything to the first row. Corresponds to saying that whatever this matrix is, the first row of it has to be 1, 0, 0. And likewise, I didn't do anything to the second row, so the second row has to be 0, 1, 0. The third row now is 0, 1 here, minus 4 here. Okay? So this, one would call, is the elementary matrix that corresponds to this elementary row operation. Okay? So this correspondence can be made even more explicit, like this. If I were to start with A and multiply it from the left by the elementary matrix that corresponds to the row operation that I made here in the first step, I claim that I should get this matrix, okay? So let me call this something. Let's call it E1, the first elementary operation, the first elementary matrix that I used. So, just going to record it. 1, 0, 0, 0, 1, 0, 0, minus 4, 1. That's E1. And A is over there. 0, 1, 2, 1, 0, 3, 4, minus 3, 8. Now let me be fast here. So recall again, these are rows, then these are columns. I'm going to get a 3 by 3 matrix. 1, 0, 0. It's going to duplicate everything. Or rather, so it's going to duplicate this entry here. 0, 1, 0. It's going to duplicate this entry here. Then the third one, for instance, it takes minus 4 plus 4 is 0. And then minus 3. Yeah. And then minus 12, minus 4, which is exactly that matrix. Okay? So really, this row operation stuff, this row reduction stuff, is just you taking your matrix, your equation, and multiplying, or scaling if you want, from the left by certain matrices. And eventually, you end up with the result. This is pretty much just like regular algebra. If you have an expression that says left-hand side equals right-hand side, what you can do is you can piece by piece try sending parts of the left-hand side to the right-hand side to solve. You're doing the same thing. So let me just write it like so. Let me call these names. Using this understanding, what we can say is the following. Yeah, so this is E1 and then E2. Then E3, then E4, E5, E6. Ends up with identity. This actually tells me the following. A, E1, E2, E3, E4, E5, and E6 equals identity. Okay, now sending all of these to the other side, I get this. A equals E6 inverse, E5 inverse, E4 inverse, E3 inverse, E2 inverse, E1 inverse. It looks complicated, but it turns out that inverting elementary matrices is rather straightforward. For instance, the inverse of this is the same matrix except you have a plus here instead of a minus. And this really is the inverse of A. Okay? So based on this idea, there's an algorithm called the LU decomposition. That is very useful, very practical. We're going to discuss it, but not now. We're going to discuss it after the first midterm, at the end of determinants, because it turns out that this is such a powerful thing and useful thing that it's also very useful to compute determinants with relatively low cost, let's say. For now, I just wanted to introduce the elementary row operations and rather elementary matrices and how they correspond to elementary row operations. Okay, this is, I think, all I wanted to say about matrix multiplication. Starting from tomorrow, we're really going to start talking about subspaces, bases, column space, and so on. Okay, thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today, we're going to start talking about linear subspaces of Rn. So this is a new term. Really, we don't really need to think about subspaces of this particular vector space. Whenever you have a vector space, you can talk about its linear subspaces, but we've got to start from somewhere, and this is where we start from. And this is the definition. A subset, so it's a bunch of vectors. S of Rn is called a linear subspace. So here the word space, instead of the set, telegraphs there is some telegraphs that there is some structure. Okay, that's what people in math use the word space for. So space. Whenever you see the word space, this alludes to there being some structure. There is some structure. And what is a structure in this case? It's a structure of linear algebra. That is to say, if your set of vectors is closed under vector space operations. That is to say, if I were to take two vectors in my set S, I want their sum to be in S as well. And if I were to take one vector in S and one constant scalar, C, then C times V, I want to be in S as well. And if you want to shorten this, you can just say S is a linear subspace if it is its own span. Right? This is a way of compressing all this stuff. Okay? It's just a definition. Of course, Rn is a subspace. Rn is a subspace of itself. Right? So let's just write a couple of examples. So Rn is a subspace of itself, trivially, because it is already closed under vector addition and scalar multiplication. I can think of, for instance, the zero-dimensional subspace, which consists only of the origin. So, okay, so 0, 0. So this consists of one vector, okay, is a subspace. If I were to take any other vector too, and if I were to look at its span, right? So span of B is a subspace. But you see, if I were to just take the set consisting of only V, so it's one vector, that is not a subspace. Recall this was the notation that we were using to denote sets. We were putting some elements inside curly braces. This is a subset, but not a subspace. Okay? And these are the basic examples, I think. Perhaps I can be even more explicit. Let's say, for instance, x-axis in R2 is a subspace. Let's try to verify this. How can I do this? Let's say that I'm denoting this x-axis by S to be complacent, to be compatible with that definition. I need to show two things, right? The first is that if I take two vectors in S, but I know, so then I know that V is something like this, A, 0, by the definition, right? It's in order for a vector to be on the x-axis, its y-coordinate has to be 0. And likewise, W is of this form. It's B, 0. And clearly, if I were to add them up, again, I would get yet another vector whose second entry is 0. which means that this is in B, this is in S. And likewise, if I were to take a vector in S and a constant in R, clearly if I were to take a vector that is on the x-axis, and if I were to scale it by some number, it doesn't matter what that scalar number is, it's always going to be still on the x-axis. So, okay, let's write it like this. C times A0, which is CA, comma 0. And this is again in S. And of course, I could have used the y-axis if I wanted. I could have used any other line passing through the origin, and that would still be a linear subspace through the origin is a subspace. You see, these are really rather explicit versions of item 3 here. I'm just taking a vector, and I'm just looking at the span of it. And this, too, is a specific case of this, because I didn't say here V is a 0 vector. Clearly, the set consisting only of the origin is the span of the 0 vector. However, if I were to take a line in the plane that is not passing through the origin, that fails to be a linear subspace. A line not passing through the origin is not a subspace, a linear subspace, not a linear subspace. How can I sort of justify this? For instance, I can think of the line, let's be even more specific, let's think of the line y equals 1. Okay? So let's say that S is the set of points in the plane, right, vectors, such that y equals 1. So S looks like this. This is S. And I'm claiming that S is not a linear subspace, even though it is a line, you see, but it is not a linear subspace. How can I verify this? Or how can I argue that this is indeed that way?
Using the checks we made earlier?
Yes, but tell me something specific. So either I want one specific vector in S such that some constant multiple of it is not in S, right? Or I want two vectors that are in S such that their sum is not in S.
What if you had what if you had the vector, I guess like 1, 1, and you multiplied that by 2, you wouldn't get 2, 1.
Exactly. Exactly, right? So you're able, so by just doing vector space operations, you can just leave S, right? So what your colleague said looks geometrically like this. He said, take this, 1, 1, right? So this vector certainly is in S, but if I were to scale this by a factor of 2, this would just leave the space. Okay, it becomes like this. So let me just write it. So V, which is 1, 1, certainly is in S, but 2 times V, which is 2, 2, is not in S. So S is not a linear subspace. Okay? Here's something interesting, though. The fact that we're still using something like a linear space, right? The only problem here really is that this is not passing through the origin. It's literally a line. So somehow it should be somewhat similar to linear subspaces. And indeed, this has a specific name. It's called, things like this are called affine subspaces. Let me write it here. Instead, an affine subspace. Okay, so this is a new terminology as well. So we're going to talk about this notion of affineness or affinity next week in the context of computer graphics a little bit. Because, for instance, when you start talking about things like translations, right? So let's say that this line is really a translate of the x-axis in this direction. So this translation is also a very useful geometric operation, but translations are not quite linear transformations, at least at first glance. So we're going to discuss this affinity stuff next week a little bit. For now, let's just leave it like this. Here's something interesting, though. If I were to take, so here's some structure. If I were to take two vectors in S, there is some is going to escape S, right? So if I have this vector, for instance, and then another vector, if I add them up, their height is going to double. And I'm going to get some vector whose height is 2. But if I were to subtract them, it's going to be in S. So A1 and then B1 is in S, certainly, for A, B some numbers. And if I were to subtract them, well, I guess it doesn't quite get you don't quite get a vector that is in S, but you get a vector that is in the direction of S. So is A minus B comma 0. This is a vector in the direction of S. This is one structure. Another structure, for instance, is that if I were to take a linear combination of any two vectors where the coefficients add up to 1, that is to say, if I take two vectors and I interpolate them, so let's say that t is an interpolation parameter. It varies between 0 and 1, and I use it to interpolate these two vectors. Okay, so let's add this up. This is ta comma t plus 1 minus t times b comma 1 minus t. And then when I add these up, I get this. And you see, this is again in S. So this sort of an operation is called an interpolation. So you start, for instance, when t is 0, right? You start at b, because when t is 0, this goes away. And you're fully at b comma 1. And then when you're slowly increasing t from 0 to 1, this slowly starts to turn into 0, and this starts to become 1. So that from b1, you turn into a1. So this is an important operation as well for many things. So this is called an interpolation. That's an interpolation. So these affine spaces, even though they are not quite linear spaces, they have certain structures. Okay? Let's look at more examples. For instance, if I have a linear system of equations whose right-hand side is 0, then its space of solutions, right? So its set of solutions is a linear subspace. So 7, 8. The set of solutions of a system of linear equations with the right-hand side 0, with so the systems of equations with right-hand side 0 are called homogeneous, aka homogeneous. System. The set of solutions is a linear subspace. Right-hand side. Linear subspace of the input space. Okay? I think this is explicit enough. Or should I do a physical or more numerical example? Okay, so let's think of this. I'm going to do a 2 by 2 system. Okay, I need 6 numbers. Tell me 6 numbers. Hmm? 3. 1. Okay. 9. One more. Huh? 5. Okay. So we can do row reduction and everything, or you can solve for x. But now that we've learned some technology, let's use it. Well, in matrix notation, this is like this. Oh, of course, I shouldn't use the right-hand side non-zero. So I need really 4 numbers. Should be 0, 0. Okay. Okay? So, but you see, this is invertible. Its determinant is non-zero. It's some number that I didn't compute, but I can see that it's non-zero. So, right, because 6 minus 24 is minus 18. Certainly minus 18 is not equal to 0, which means that this has an inverse. I don't need to really compute it, because I know that I can send it to the other side as using its inverse. And again, I don't need to compute this, because no matter what this matrix is, the end result is going to be 0, 0. So the space of solutions of this system really is this. Let me write it here. It consists only of the 0 vector. Okay? Which is this case. Okay? Now, let's change the numbers a little bit so that it is not invertible to see some other situation. So what can I do here? I can say, for instance, if I were to change this 1 to a 4, then the matrix would end up being non-invertible. Let's do that. Yeah, okay. So this is, I guess, let's call this 9, and then I have a 10. Okay, in matrix notation, the left-hand side matrix is 6, 8, 3, 4. The determinant is 24 minus 24, and now we know that that means that the matrix is not invertible. So I can't quite do the same thing there, okay? But what I can do is I can realize that the second row, rather, the first row is twice the second row. And so, or let me just do row reduction. In fact, I can do this. Okay. And cashing out the solution, this says that 3x plus 4y equals 0, right? We ended up with the same thing, of course, because the first row is nothing but twice the second row. There's nothing super complicated going on here. But what can I do further? I can say, for instance, here, because this is the pivot point, pivot entry, I'm going to think of the second second variable as a free variable. So really what I want to write is something like this. 3x equals 4y, 3x plus 4y equals 0, and y is free. And in fact, let me write it like this. Let me go one step further. Turn this into 1, 4 over 3, 0, 0, 0, 0, which then says that x is equal to minus 4 over 3 times y, and y is free. Okay, that's the solution. So if I wanted to write this using sort of like a set notation, I could have written it like this. So the set of solutions, right, equals x comma y pairs in the plane such that this expression holds. So x is equal to minus 4 over 3y. Okay? Now, from this, I can, for instance, say that this is really the span of one vector. For instance, I can use minus 4, 3. And we did discuss the fact that spans of vectors is a linear subspace. Of course, you could go ahead and use the definition as well, but you see, these sort of more structural examples allow you to sort of argue about things faster. Does this make sense? And of course, this is yet another special case of item 6. And also note that if I had here non-zero numbers, then something very similar to what happened here would happen. If I had a non-homogeneous system, then its space of solutions would be an affine subspace. Let me record that as well. 11. If right-hand side is not 0, then the space, well, then the set of solutions is an affine subspace. Okay? Exactly the same phenomenon that happens here. Any question? Here's a nice example. Here's a nice exercise. Come up with a system of two equations with two unknowns, with right-hand side non-zero, such that its solution set is this line. Okay, this is a nice exercise. I want to leave it to you. Where should I write it? I'm going to write it there. So you see, in math, it's quite about the way you're looking at the things. What is the problem and what is the solution? Maybe sometimes the solution is the problem and the problem is the solution. It's all a matter of how you see it. Find a system of two linear equations with two unknowns whose solution set is the affine subspace that is y equals 1. Whose solution set is the affine subspace xy such that y equals 1. Okay. Now you should immediately say to yourself, I have 6 numbers I need to figure out. 4 for the left side, 2 for the right side. The numbers on the right side cannot be 0, because if it did, this would end up passing through the origin. So I need 2 non-zero numbers here. And here on the left, I need to use some numbers such that when I look at the matrix, the determinant is 0. Because if it weren't, the solution wouldn't be a line, it would be a point, as in this case. Okay? It's a very nice exercise. We can argue about this algebraically or geometrically. Of course, there are multiple solutions to this. Any questions about any of this? This is just a barrage of sort of examples and ideas. Good? Okay. I want to introduce 2 perhaps more upscale ways of coming up with linear subspaces, constructing subspaces, or how you might encounter them. And these 2 ways are really about linear transformations and how I can use linear transformations to come up with new subspaces. So let me just say example again. It's a separate example. Let's say that I have a linear transformation or matrix. So I have a linear transformation from Rn to Rm. In other words, I have an m by n matrix. Okay? AKA, A is a matrix of dimensions m by n. Now, if I have a linear subspace of the input space, Rn, then I can apply A to any vector in that subspace, and I would get something, a set, in the output space. That collection of output vectors is a subspace, is a linear subspace of the output space, and vice versa. So, if S is a linear subspace of A of Rn, then its image under A which is denoted by A of S. So you pretend that S is a vector itself, but it's just this is like an abusive notation that is very common. Then its image under A is a linear subspace of Rm. Okay? Yeah, so this is denoted like this, A of S. And how can I write this? I can say that using set notation, this is A V such that V in S. Okay? So you took your linear subspace and applied a linear transformation to it. It goes somewhere else, but what I'm saying is that that output, this new image, too is going to be a linear subspace. So this is the idea that linear transformations preserves lines. Linear transformations takes lines to lines. Of course, more generally, linear transformations take planes to planes and so on. So this is the idea. Lines to lines, and so on. This is, of course, not quite accurate because a linear transformation can take a line to a point. It can just collapse everything to the zero vector, but this is sort of like the dictum. Let's try to verify this. So I need to check two properties. That if I were to take two vectors in A of S, then their sum too is in A of S. And likewise, if I were to take one vector in A of S and scale it by some number, then that scaled vector too is in A of S. Of course, we need to be careful about inputs and outputs. Okay? So check. So if I were to have two vectors in A of S, maybe I should use a different notation. Let's say PQ. Then by definition, so these are two outputs. I know that there are some inputs in S that A sends to these two vectors. Then there are some inputs B and W in S such that A of B equals P and A of W equals Q. But then P plus Q is AV plus AW, which is the same thing as A of V plus W. But then I know that V plus W is in S. It's an admissible input because S is a linear subspace. Okay? So this is in S, which means that this vector is in here as well. So think of it like this. When we started in the beginning, we said that my input space is Rn. But for whatever reason, you have a situation at hand and you want to really restrict your input space to a certain subspace. What this is telling you is that you can still do linear algebra. It's not a big problem. Okay? Now you verify that scalar multiplication holds as well. I'm just going to leave that because it's the same idea. I'm just going to leave it as an exercise to you. Verify scalar multiplication is okay. Okay, so this is one way of generating linear subspaces. I can take a linear transformation, take some subspace in its input space, and push it forward using my linear space, a linear transformation, to generate a linear transformation, linear subspace in the output space. That's one. I can do it backwards as well. That is to say, if I had a linear subspace in the output space, I can pull it back using my transformation. So that's the first. Oh, this is one. That's one, I guess. Here's another example. Well, I don't want to split the examples actually. These two are the same idea actually. So that's one. And then two. If t we're using for transformation. Let's say if S is a subspace of the output space or M, then it's what is called preimage under A. Is a linear subspace of the input space. And instead of output space, input space are n. Instead of A of S, now you write A to the minus 1. This doesn't mean that A is invertible. You just say that you're going backwards. Okay? So these are all those vectors V in Rn, such that the output is an S. Okay? And the verification that this is indeed a linear space is pretty much the same way as this. I don't think we need to spend too much time on this. So you can take a linear subspace, push it forward, pull it back using a linear transformation. Okay?
Preimage is like what it's before we do the transformation, right? Like what's a preimage?
The preimage is something like this. You have a system. Your system is giving your linear transformation. And somehow, for whatever reason, you have a certain specified set of outputs. Those are the things that you're interested in. And you're really interested in those specific outputs. So now that you have that, you want to figure out what are the inputs that would allow you to produce those outputs. Okay?
So it's like going backwards.
Exactly. Yes. Yes. Yeah, this gets confusing if you start thinking of this temporally, okay? Any other questions about any of these?
A inverse of S is the preimage.
Yes, yes. Let me just note here, this is a big warning, this notation doesn't mean that A is invertible. Okay? Maybe it would be a good idea to do some geometric examples.
The preimage, is the inputs findable, or like the preimage findable if it's not invertible?
Yeah, yeah. Yeah, you can always solve the system. Yeah. So let's think about 2-by-2 transformations. In that case, the only specific, or the only sort of non-trivial examples are the lines passing through the origin for subspaces. So consider this. Let's say, for instance, my matrix is, well, A equals 0, -1, 1, 0. Recall that this is a transformation that corresponds to rotating the plane by 90 degrees in the counterclockwise direction. Okay? So let me just record this super fast. So if I had two vectors, so you see 1, 0 goes to 0, 1, 0, 1 goes to -1, 0. Okay? Rotate by 90 degrees in the counterclockwise direction. So what's a subspace that I can look into? For instance, let's look at this subspace. It's even better. So let's look at the x-axis. Okay? So if S is the x-axis, then I'm saying that under this transformation, it's going to turn into something else. And whatever that is, that collection of vectors, 2 is going to be a linear subspace. But of course, what is A of S? It's a bunch of vectors, right? But how can I think of what A of S is? So think of applying your transformation to not only one vector, but the whole collection, the whole shape. Exactly, right? So now it's the y-axis. Became this. This is S, this is A of S. It's the whole thing. It's not just one vector, two vectors, it's the whole thing. Let's do another example. For instance, if I were to have in the output space, let's say I have this. Okay? Let's use another letter. L. Okay? So L I can write, for instance, is this. X comma y such that y is equal to x. So it's the main diagonal. How can I think of A inverse of L? What is this?
I think that it's the line minus y equals x.
Exactly, right? So if you're going from here to there by rotating like this, well, in order to go back, you need to rotate this way. And so it becomes this. Okay? And you can write it down if you want. So this is xy such that y equals minus x. Okay? So this is the idea. Does this make sense? All I wrote over here and there is that these ideas apply for any linear transformation from any input space to any output space, no matter what the dimension of these subspaces that you're looking at. Okay? If I had a three-dimensional input space, and if I chose a two-dimensional subspace of it, which is a plane, then the output would be a linear space as well. Okay?
Is that A inverse of L?
Yeah, yeah. I mean, that's how I'm writing it, but so this is sort of like the term, this is the notation. Yeah. There are like more sophisticated notations that really separate distinction between a vector and the space of vectors, but I think this is more common, so that's why I wanted to introduce this. Okay?
So all those are subspaces of xy space.
Yes. Yes.
How do we get the A inverse?
Okay. This, it's an abuse of notation. Here, I'm not really saying, so wait, sorry. Ask again.
What is the A inverse? Like, how did we get that?
It's just a preimage symbol.
Yeah. It's just a notation. I'm saying, here I'm saying I'm taking a subspace, applying the transformation A to it. Here I'm saying I'm taking the subspace L, applying A in the backwards direction. Yeah. So now we're not really going to use these things that much, but we're going to use specific cases of them. I still have time. Let me introduce them. And these are the so-called null space of a transformation and the column space of a transformation. Okay? So there's something psychological going on at this stage. Because so far we were thinking of some input space, some output space, and the linear transformation after. But now we're really shifting the focus on the transformation itself. We're saying, oh, instead of thinking of the output and input spaces, we should really think of how things transform and talk about the inputs and outputs with reference to the transformation. Recall in week 1, in the first class, when we were talking about PageRank, I also said something that is similar, in a sense related to this idea. Instead of looking at the point, looking at the web page, you're looking at how it is being transformed to other web pages. So the transformation is more important than the thing itself, than the vector.
Then you have like a square section of the xy axis.
Uh-huh.
XY plane.
Yes. So it's a quadrant, right?
It's a, you know.
Oh yeah, okay, it's a box.
Subspace, but it wouldn't be a linear subspace.
Yes.
So then you get into nonlinear subspace.
Exactly.
Or
Yes.
In R3, would that just be a field, I guess?
Say again?
In R3, would that just be like a field?
I mean, I wouldn't use that word, but in R3, you can either have the origin, which is this zero-dimensional subspace, or a line passing through the origin, or a plane passing through the origin, or everything. Yeah. Okay, so let me introduce this terminology. The null space of a matrix or a transformation of A, let me just use this, of A from Rn to Rm is A inverse of 0. So all the vectors in the input space that is sent to 0. And this is, so we're going to use this notation, null of A. So this is more general. This is like more specific. This space is so important that it has its own notation. And the column space of A is the image of everything, is A of Rn. And this too is very important, and that's why it has its own notation. And we're going to call this call of A. Okay, I'm out of time. But tomorrow, we're really going to start focusing on these two spaces and really sort of tie all this to what we've discovered, what we've talked about so far. But I think this is all I wanted to say for today. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today, we're going to keep working on these two subspaces that you can attach to a given linear transformation. Above, I wrote this general definition. We discussed this yesterday, but these are special cases of the above definitions, but these are really the things that you really need to get comfortable with. And once I sort of discuss a little bit these spaces, I'd like to do an example, a numerical example where we can sort of see how everything is working out. So first of all, just a recap. If I have a linear transformation or a matrix, right, from Rn to Rm, and if I have a subspace, linear subspace of Rn, the input space, and a subspace of the output space, then using my transformation, I can take that subspace K of the input space and push it forward using A. Yesterday we called this image. It's the same thing. Push forward is also a very common phrase, and this has applications in, this has sort of reincarnations in different fields, but this is sort of like the general idea. You take, oh, of course I made a mistake. A of k, let me use red here because red is, according to this board, things coming from the input. A of k is just going to be AV, that's going to be an output, it's blue, such that the input is specified to come from that specific subspace. Okay? Let me do this as well. And if I were to do it the other way around, if I had a subspace in the output space, using my transformation, I could pull it back to the input space. And so the way I would write it is like this. So preimage of the subspace L under A is the space of all those vectors in the input space such that they're sent under A to this specified space of outputs. Okay? Now, if you were to specialize the case when K is equal to everything, so it is Rn, you get, instead of this general image, you get what is called the column space. Okay? And likewise, if you were to take this and if you were to specialize the case of L being the zero vector, the trivial subspace, you get back the null space. Okay, so let's try writing this. Let's try describing this space using something different. Well, by definition, let me do a two-dimensional example. So consider this. Let's say that I'm going from R2 to R2. Okay? So now the column space, let me just write down the definition. The column space of A is nothing but the image of R2 under A. And according to our description, I can write it like this. A, xy, xy arbitrary. Right? And let me put numbers. Let me have a matrix for my matrix. So let's call it ABCD. Okay? And I can write this down, right? I can write it like this. This is, so let me write it here. ABCD xy is, so AX plus BY, CX plus BY, which then I can split like this. X times AC plus Y times BD. Okay, so this expression is the same thing as, so I can write the set like this. X times AC plus Y times BD, XY arbitrary. what can I say? What other phrase can I use to describe this set now? Any ideas? So this expression has a specific name, and so does this. We've seen this in week 1, really. What is this? What can I? How can I call? Like, what can I call this expression?
It's like a vector equation.
It is a vector, yes, but I want to refer to A. More specifically, I want to refer to the columns of A.
Is it like page rank?
Say again?
Page rank?
No, no. It's not as complicated as that. What is this expression?
Transformation?
It is a transformation, but I want something more specific.
Scale? Scalar?
This is scalar, but what is this? It's a vector, but I want to refer to A. I can say that this is...
Is that like the identity matrix?
Not quite.
No.
We don't know what the matrix is. I can call this a linear combination of columns of A. Right? And I can call this the span of columns of A. I am literally allowing any single linear combination here, right? So this is an arbitrary linear combination of columns of A. And this is really the span of the columns of A. Okay? So literally, column space of A is literally the space of columns of A. Okay? So let me write it like this. This is also the span of columns of A. That's why it is called the column space. Okay? Does this make sense? Okay.
What is A, C, B, and D in this, in that linear combination?
Well, what they are not really important. What is important? So they are arbitrary numbers. What is important is that this vector has a source, right? Its source is this, and this vector also has a source. That is what is important. A, B, C, D could be any number you want. This applies to any linear transformation whatsoever, as long as they're 2 by 2. My point is that the same idea applies even if the output and input dimensions are different, large, and so on. The same idea, right? So if you want, you can write it down. It just takes slightly longer. Okay? Any other questions about this? Okay? So another way of thinking about this, of course, is that we've also discussed how any such linear combination, so it's the column space, I can also think of it as this. If I were to put some outputs, if I were to choose some outputs, so A, B, C, D, X, Y equals U, V for U and V fixed numbers, so it's a fixed output, has a solution only when, because this is a linear combination, this is in the span for fixed output. UV has a solution xy only if well, because this is a linear combination of the columns, uv is in the span of columns of A. We've also discussed this before. I'm just repeating. Just so that we can tie a bunch of these terminology together. So I can also think of this column space as, the set of all those outputs, so the set of all those right-hand sides that I can solve the equation for. All right-hand side vectors, let me call it B, such that one can solve AX equals B for X. X is an input, of course. Rn and B and R M. Okay? And you see, this really gives you a computational way to talk about, to think about column spaces. You see, at the end of the day, I introduced some terminology, but at the end of the day, it again reduced to essentially solving a system, which means it reduces again to row reduction. Okay? Any questions about this? Okay, so this is the column space. The null space, okay? Let's do a similar analysis for the null space, starting from this definition that I started with. Okay? Okay, again, I'm going to look at a 2x2 matrix. So its null space is by definition the preimage of the trivial vector or the trivial subspace. Okay? Writing out that definition over there, this is nothing but this. This is xy, so it's in the input, such that axy equals 0, 0. Now, how can I then express this set? Any ideas? What can I say? The set of all such xy's.
Isn't this like the x and y have to be 0? So it's like
no,
linearly independent?
They don't have to be 0. What is the set of all vectors xy such that a of xy equals 0, 0? Hmm?
Those are like the trivial solutions or something close.
You're getting close, yes. All I can say, so I can simply say that this is the space of solutions of ax equals 0, right? A times some vector equals 0. It's a linear system, and I'm looking at its space of solutions. Now, the output is fixed as opposed to the column space. Okay? So this is nothing but of AV equals 0. Okay? So you see, to compute the null space of a matrix, again, all you need to do is to set up the equation and solve it. That's all there is to it. This is the space of solutions x in the input space such that ax equals 0. Okay? These are the two important subspaces. Now there are two more. It turns out that it is important to look at the column space of A transpose and the null space of A transpose. So with these two, you get now 4 subspaces. These 4 subspaces turn out to be very important. We're going to discuss those other 2 as well and how they are related to these 2. But for now, let's just focus on these 2 subspaces. Okay? And let me just say, I'm just paraphrasing the stuff that we discussed the first 2 weeks using some different terminology. Okay? Any questions about any of this?
You know, if we pull back a little bit,
Yes.
look at the overall scene.
Mm-hmm.
It looks like different terminologies that have the same fundamental concept of transformation.
Yes.
So why, where are we going with all those different points of view?
Yeah, I was thinking about this yesterday too. This is, I think this is a testament to the richness of the language. Okay, it's just that you have a bunch of like synonyms essentially. So if you were learning a language, you wouldn't be like, oh, I just need one of these words. I don't need all the other words that mean the same thing. Okay, that's one way of answering this. Another way is that for whatever reason, so linear algebra is a universal tool, but what people call certain things change from discipline to discipline. And so since this is an introductory class, I think there's an emphasis as to all these different terminologies and how they relate to each other. I could say that too. I mean, agree or disagree. But I should say that especially when you're first learning about these stuff, what's going to happen is that one of these sort of sets of terminologies is going to be more intuitive to you. So I would suggest just trying to figure out which sort of notation or which terminology works best for you, and then think of the other ones in terms of the one that is more natural to you. And then over time, you sort of start using the other ones as well, and it starts making more sense. Yeah, when I was first learning this stuff, so it's like transpose, for instance, it didn't make sense to me. There's a way of handling this without using matrices whatsoever. But over time, you end up needing to learn.
So some of those terminologies are more applicable to certain disciplines.
Yeah.
And you prefer using this.
Yes. So there are certain mathematicians, for instance, who are like looking at this and they say, column space of a transformation, but a transformation doesn't really have a column, right? I would like to be able to talk about that space without referring to a column. Okay, so that's why they come up with different things. But then there's someone else, and so for instance, they call the column the image, like I did over there. But then some people are like, what is the image? It's literally the space of columns, right? So perspectives change depending on the area, depending on the field, depending on the paper that you're reading or book that you're reading. So, okay, yeah. Any other questions? Okay, so now let's do a numerical example and really start using these ideas to talk about the null space and the column space. This idea and this idea, these two ideas. Okay, so here's the matrix. So 1, minus 3, 4, minus 4, 6, minus 2, minus 3, 7, 6. This this is a 3 by 3 matrix. So it has a 3-dimensional input and 3-dimensional output. Okay. Of course, the question is, what is the column space and what is the null space? Well, both of these, at the end of the day, once you write everything out and so on, ends up being about an equation where on the left-hand side you have a times a vector, and here as well. So you might as well, even if you're sort of like confused, you might as well just row reduce this, okay? Okay, so let's do row reduction. And now that we're doing row reduction and we discussed the elementary matrices, how they correspond to elementary row operations, let me also try to write it in terms of those as well, okay? So what I can do, for instance, here is this. I can take the first row, subtract 3 times the first row from the third row, or sorry, add 3 times the first row. And likewise, I can do the same thing with the second row. So this is my, actually, let me do it like this, okay? I'm just going to call the matrix that corresponds to this row reduction E1 and record what E1 is somewhere else. Okay, let's do it like this. It'll be better. Okay. Is this correct? It's not. So the first operation is this. Okay? If I were to apply those operations, now I get a new matrix. 1 minus 3, 4. So here I have 0. I'm adding 4 times the first row to the second row. 4 times minus 3 is minus 12. So this is minus 6. 4 times 4 is 16, so this is 14. And then add 3 times this to this. This is 0. Now this is minus 2. And then this is 18. Okay? Is this correct? Yeah. Okay. I did this earlier and came up with a different, maybe my numbers are wrong. Hang on. Okay, yeah, sorry. What is the case is that this should be a minus, so that this is minus 18. And then this changes as well. 3 times minus 4 is minus 12. Add to 6, minus 6. Okay, you see now it's much easier. So now, next stage is going to be E2. I can do, for instance, the following. I can multiply the second row by minus 1 over 6, and then the third row by minus 1 over 2. I'm going to record it over here. Replace R2 by minus 1 over 6 times R2, and replace R3 by minus 1 over 2 times R3. Okay, so now once I do that, I get this new matrix. This is now 1 minus 3 minus 4. This is 0, 1, 3, 0, 1, 3. And then what I can do is I can take the, for instance, second row, subtract it from the third row, and let me actually finish this and get the reduced echelon form. Again, I can take the second row, add 3 times it to the first row to get rid of this as well, so that we have the reduced echelon form. And I'm going to combine both of these operations into one matrix. Okay, so this is E1, E2, E3. R3 replaced by R3 minus R2. R1 replaced by R1 plus 3 times R2. Now, once I do that, I get this new matrix. Second row stays the same. This is 1, this is 0. If I multiply this by 3, it is 9. Add to minus 4, it's 5. And then the third row is zeroed out. Okay? Any questions about this? Again, this is week 1 row reduction. And indeed, this is a reduced echelon form. And recall from week 1 that any matrix has a unique reduced echelon form. Let me call this new matrix U for upper. It's upper triangular, so I'm going to call it U. So this matrix is U. Okay? Now this row reduction, if I write it in terms of matrix multiplication, recall that, for instance, applying this row operation to A really is multiplying A from the left by this. Okay? So I have an equation really. Should stay here. I can erase that. Why shouldn't it?
I don't know. I always thought of the same number of columns as different rows.
It's an array of numbers. So matrix language, so matrix algebra is the assembly language of linear algebra. Okay, everything, in computer science people say everything is a 0 and 1 at the end of the day. It's the same thing. Everything is a matrix underneath. Matrix is cognate with words like mother and material, okay? Okay, so writing this out using or interpreting, thinking of these as matrices by themselves, I can write this row reduction like this. A, E1, E2, E3 equals U. Okay? Which means that if I were to send each of these matrices to the other side, because these are invertible matrices, right? Because if I can go from this stage to this stage by doing a row operation, certainly I can go back, right? If from here to there, I'm going by adding 4 times the first row to the second one, the way I can go back from here to there is by subtracting 4 times this row from this row, okay? This is invertible. All of these operations are invertible, which means that I have this. E3 inverse, E2 inverse, E1 inverse, okay? And I'm going to call this part L. So L is this new matrix, E1 inverse, E2 inverse, E3 inverse. Now, I know what U is. Let's compute what this is. So in order to compute this, first I need to transfer or translate those row operations into matrices, and then I'm going to need to invert them. Okay? Now, here's what I can think. Here's how I can think about. Recall that the left side here is the new rows, and the right side is the old ones. And I'm thinking of R1, R2, R3 as the entries of a column vector. And if I were to do that, I would get this. So for instance, E1 doesn't do anything with the first row. That's why it should be 1, 0, 0. It should start with 1, 0, 0. Second row, it is 4 times the first row times plus 1 times the second row, and then I'm not doing anything with the third row. And likewise, the third row is 3 times the first row plus 1 times the third row. Okay? So this is the matrix corresponding to that row operation. If you don't believe me, you can just take this matrix, multiply it from the left, and you're going to get this matrix. Okay? That's E1. E2, again, if E2 is scaling the second row by 1 over minus 6, that means that in the middle I should have a minus 1 over 6. And likewise here. Again, if you don't believe me, you can take the second matrix, multiply it from the left by that matrix, and you're going to get this matrix. Okay? And then the third one is there. It's the same idea. The second row stays the same, so in the middle I should see 0, 1, 0. The first row becomes like this, and then the third row becomes like this. Okay? Any questions about this? This is an important thing to be able to do. Row reduction, elementary row operations, and the corresponding matrices.
E3, would the 3 go in the second row? Since you're doing 3 times.
Oh yeah, sorry. Thank you. Yes. Okay? Thank you. So this is that. Now let's think about their inverses. I need an inverse for this. I need an inverse for this, and I need an inverse for this third guy. And certainly, these are 3 by 3 matrices. Their inverses are going to be 3 by 3 also. So I need 27 numbers. How can I come up with these numbers? Well, we learned an algorithm to solve, to find the inverse of a matrix, right? You sort of started with E1 times something equals identity, and then you augmented so that now you have E1, and then next to it you have identity, do row reduction, and at the end, if you can get on the left-hand side the identity, on the right-hand side you have the inverse. We discussed this. And you can indeed use this method to compute the inverses. But these matrices, there's a reason why they are called elementary. These are really rather straightforward to invert. Okay? So you can really eyeball these entries as well. And here's how you can do this. Raise that as well. So let's start with finding this guy. So 1, 0, 0, 4, 1, 0, 3, 0, 1. I have this unknown 3 by 3 matrix, but I want it so that when I multiply these two, I get the identity matrix. Okay? Now, recall that when I have a matrix multiplication, the left one I split into rows. The right one I split into columns. Okay? So now the idea is this. Let me first try using this first row. I'm going to take this and multiply it with these 3 rows, these 3 columns. But you see, these 2 entries are 0. So no matter what I put in these entries, it's not going to affect the end result. The only thing that's going to affect the end result are these entries. And I know that if I were to take this, multiply it by this, I get 1. Which means that this number has to be 1. Does this make sense? It's almost like Sudoku. I'm sort of like trying to figure out what should fit. And again, taking this, putting it here, I get 0, which means that this number has to be 0. Likewise here. How about this? What can I say about this entry using the same idea? So this entry, how does it affect the end result? I take this and multiply it by this, and I get 0, for instance. Exactly, right? Because from here I get plus 4. But in order for the end result to be 0, and because I can't use this third entry here because of this, the second entry has to be minus 4. Okay? And likewise here, minus 3, 0, 1. So that's the inverse. Okay? So we talked about these long operations, long procedures to compute things, but eventually, so ultimately you should really start seeing patterns and how to sort of like how to come up with, so you need to learn how to use shortcuts and heuristics. And here too, for instance, like let's look at this. Minus 1 over 6, 0, 0, 0, minus 1 over 2. Same idea. This has to be 1, 0, 0. How about this entry, for instance? The end result is this. Right? So this has to be a 0. Because you see, to get to this entry, I'm going to use this row. So the 2, 1 entry comes from the second row of the left one and the first column of the right one. And if I look at this guy, these 2 entries are 0, which means that these 2 are not going to matter. The only thing that I can somehow do something so that I get 0 at the end is to kill this. The only way you can kill this without using these 2 is by putting a 0 here. Okay? So that's minus 6, same idea because I want a 1 at the end. There's a 0, and then 0, 0, minus 2. That's the inverse of E2. Okay? And again, it makes sense because E2 came from here, right? We took this and scaled the rows, second row by some number, third row by some number. How can I go back? Well, scale these rows by the reciprocals. If you're going from here to there by dividing these 2 numbers by minus 1 over 6, well, surely you can go from here to there by multiplying these numbers by minus 6. Okay? So this is the second, the inverse of the second matrix. And finally, let's do the third matrix. the main idea is that whenever you have a matrix, so this is the broad idea, whenever you have a matrix that is so-called sparse, it has lots of zeros in the entries, it's rather straightforward to use it and do things with it. Right, because when I'm sort of doing this eyeballing, I'm really leveraging the zero entries here. If I didn't have all these zero entries, it would be much harder to guess things. Okay, so in order for this to be 1, I need 1 here, and then, oh, can't quite say this actually. Okay, let's start somewhere else. This has to be 0. This has to be 1. This has to be 0, for instance. And then if I were to have here, so if I were to look at this, I don't know what to put here, but what I can put here is, for instance, because this is going to generate -1 and I want a 0, this should be a 1. Okay? And then there's an issue. Oh, because this is a 1. Okay, now it works. Okay, so now it works. Good. That's a 0. This is a 1. And then in order to get 1 here, I need to put 1 here. Now there's the first row. These two are 0. In order to get a 1 here, I need to have a 1 here. These two are 1, 1. And I'm multiplying this. So 1 times this plus 3 times this, I want to be 0, which means that this has to be -3. And then finally, 1 times this number, 3 times 0 plus 3 times 0. So whatever this number is has to be 0, which means that this is the 0. This is the entry. Okay? Of course, what is the pattern here? Yes?
Is it the case where like E1 and E3 are both just addition? And so in both E1 and E3, they're basically the identity matrix, but then you like negate the stuff that's not in the diagonal?
No matter, yes, there's a pattern there. No matter what row operation you do addition at the end. What is the pattern is that you have ones on the diagonal. Yes. It is indeed true, you see. Now that you have this, if you have a lower triangular matrix, the way to invert this to get that is to put minuses here. Okay? In any event, we have these 3 matrices. So now, once I have these 3 matrices, I can multiply them to get this L. Okay? Let's do that multiplication. So that's E1 inverse, E2 inverse, E3 inverse. Now what is this? Let's first multiply these two. This is E2 inverse, and then E3 inverse is 1 minus 3, 0, 0, 1, 0, 0, 1, 1. And I multiply this. Right, I have a 3 by 3 matrix. This is 1 minus 3, 0, 0, minus 6, 0, 0, 0, minus 2. Okay? Oh, times E1 inverse, of course. And then when I multiply this matrix as well, now I have this. This 1 minus 3, 0, 0, minus 6, 0, 0, 0, minus 2. And you multiply this, you get this. 1 minus 3, 0, and then minus 4. 12 minus 6 is minus plus 6, 0, minus 3, 9, minus 2. So that's L. Okay? We have 5 minutes. Good. Any questions about this? I just multiplied these row operations to get somehow this matrix. Now the claim then is that A equals this matrix that I computed times U. Okay? Let's, just to make sure, let's do this calculation. I'm going to leave this here. Recall, the problem is to figure out the null space and the column space. This is leading there. I just wanted to do this example very explicitly. Because there's something confusing happening when you try to do row reduction, when you try to use row reduction to come up with the column space. So A equals LU, allegedly. Let's check it. So if I were to take that matrix and multiply it from the left, or multiply this reduced echelon form from the left by that matrix, I should get back my original matrix, right? So LU is 1 minus 3, 0, minus 4, 6, 0, minus 3, 9, minus 2. 1, 0, 5, 0, 1, 3, 0, 0, 0. It's a 3 by 3 matrix. 1, minus 3, minus 4. Minus 4. This is a stunt, of course. I know that it's going to end up being a 6, and then minus 20 plus 18, minus 2. Good. Minus 3, 9, minus 15 plus 27, 12. No? Made a mistake? Oh, sorry. Is there a mistake here? Oh, I made a mistake. Minus 15 plus 27, 12. I have a factor of 2 error somewhere coming. Does anyone see where I made the mistake? Huh. Okay. Well, I guess we're going to talk about this tomorrow. Yeah, okay. I did this correctly on paper. This number is wrong. Okay. Okay. For some reason, this number should be 7. Okay. I'll cover that tomorrow. Thank you. This is leading somewhere. Tomorrow, we're really going to use this to talk about the null and column spaces of this matrix. Thank you. See you tomorrow.
It's because when you did that, yeah, it's the minus, yeah, like the bottom row times the second column, like right where you're pointing your hand, like minus 3 times minus 3 is 9, and then 0 times minus 6 is 0, plus 1 times minus 2 is minus 2, so 9 minus 2 is 7.
No, but like this is not there, you see? You're using this one, no?
Am I tripping?
Oh, it's on the key one times
I made a mistake somewhere here, okay?
0 is minus 2.
Here?
Yeah, right there. I think. Yeah.
Oh, yeah, because this is a 1, this should be a minus 2. Okay, now it works. Sorry, let me just put here minus 2. So that's a minus 2, which means that this is a 7, which means that this is a 7, which means that when you multiply this and this, well, I mean, the numbers should be slightly different, I think. In any event, I'm going to tell you the correct numbers tomorrow. Thank you. Okay, let's start. Good morning. Today, I want to finish this example that we started on Wednesday. We did most of the calculations. So now, our aim is going to be to interpret and use these calculations. So I was able to factorize A as L times U, where U is the reduced echelon form of A. Recall that that's unique, and L is the bunch of row operations assembled, put together into one matrix, which is this. Last time I made this error over here, but now this is correct. Before I go into that, I wanted to mention two things. So first, we have our first midterm next Friday. So there is no problem set this week, but later today you're going to be able to see a document where I put a bunch of practice problems, because so far we only had 3 problem sets, but there's going to be questions about this column space and rank space, column space and null space of a matrix and whatsoever, and all that stuff. So for that, it's going to be good. And the main thing is that the basic problem that you should really focus on for the first midterm is that you're given a linear system of equations. You should be able to sort of do the full diagnostic, right? Find the solution, find all solutions, find the reduced echelon form of the augmented matrix or the left-hand side matrix, compute the column space, null space, compute the rank and nullity. These are terms that we're going to learn today of the matrix, and so on. If you have a row operation that you used, rewrite it as an elementary matrix, and so on. So, and in that document that I'm going to post later today, you're going to have a bunch of those problems that you can work on. Another thing, this is a second item, is that I think in week 1 I said that eventually I'm going to set up a time for the office hours, but it seems like this is working much better. So far I've been meeting 3-4 hours every week. So people, yeah.
With like the document you're sending out with like different problems, are you going to have like a list of what we should do too? Kind of like how you just went over.
Yeah. So the format is this. Take any linear system that you want,
Okay.
and there are like 52 problems. Okay? It's just like generic. Some of them are just like very basic problems. Like one problem is like how many equations are there? These are so that you sort of like keep in mind whenever you see a system, these are sort of like, this is sort of like a checklist in a sense, but it is redundant. And once you sort of start going through these problems, you're going to start seeing patterns. That's what I want. It's like, oh, you know, the answer to this question actually is the answer to this question too. These are not really different questions.
Will you have it like written down though, like you should know how to do column space, you should know how to do like, does that make sense? Kind of how you just went through and you're like, you should do this, and this.
Yeah. I mean, not in the.
Down, or will it just kind of be like a, you should know that that's what this is doing?
Oh no, I didn't write something like that. It's just that in question format. There are just a bunch of questions that you should be comfortable answering. Yeah. The second one is that it seems that just setting up appointments seems to be working better. So and a lot of you have been sending me emails, and we've been setting up appointments. It's been pretty good, I think. And so you can sort of set up appointments like that, or if you want to meet, if you want one of your colleagues or a couple of your colleagues with you, you can sort of like join forces and become a group like that, and we can sort of come up with a time and place that way as well. So if you were waiting for sort of specific office hours, just send me an email and we'll set up a time instead. Okay? So that's that. Any questions about these two? Okay, so this is what we did last time. I started with this 3x3 matrix, and we did row operations, and eventually we were able to find that its reduced echelon form is like this. And certainly this is in reduced echelon form. And of course, there are many ways to reduce a matrix. There are multiple sort of paths using elementary row operations that end up at the same reduced echelon form. Recall that the reduced echelon form of a matrix is unique, whereas the echelon form, which is slightly more general, is not necessarily unique. So even though the end result is unique, the path that takes you from A to U is not necessarily unique. In any event, on Wednesday, we had used 3 different row operations in this order. And I didn't write these down explicitly, but there were 3 of them, because that is not quite important. And then these are invertible, so I can send it to the other side, all 3 of them, in the correct order. So you see, if I want to send all these to that side, because matrix multiplication is not commutative, right? The order matters. First, I need to send this. I need to first peel off this layer, and then this layer, and then this layer. That's why first I'm seeing E3 inverse, and then E2 inverse, and then E1 inverse, instead of the other way around. And then I call this product of 3 matrices L, and so that A equals L times U. So this is a factorization, if you want. I factorized my matrix A into some invertible matrix times its reduced echelon form. And once you do this multiplication, you get this matrix. And just for perhaps more, just for the sake of being more explicit, I also computed the inverse of this. Well, if L is this, certainly this has to be its inverse. Okay, so I can multiply these 3 to compute the inverse of L as well, and it turns out to be this. So if you want, you can think of L inverse as that one sort of composite row operation that in one step takes A and turns it into U. All this is saying is that, oh, really, you should be taking -1 times the first row and subtract it half the second row and put it back into the first row. Okay? This is what really the row operations that we used on Wednesday last time gives you, or gives us. This is just a composite of all 3 of these row operations. Okay? Any questions so far? There's nothing new so far. So the point was that somehow I would like to be able to use these 2 matrices to talk about the column space and the null space of A. Now, let's think of it as transformations. So this is a matrix equation, A equals L times U. But if I think of these as transformations, really what this is saying is that A is one transformation that I can factorize. Instead of using A to transform things, I can first apply U, and then on top of that, L. Okay? So let me draw a picture. And these are 3 by 3, all 3 of them. And that means that always the inputs and outputs are going to be 3-dimensional. Okay? The way you should think about this is that this is one transformation, and this is something like the back end, okay? And this is the front end. So here, U really contains all the core of your transformation, whereas L is really about the aesthetics, okay? And so we'll think about this a little bit more to really understand. Let's start with the null space of A. Now recall that the null space of A is really all those vectors in the initial input that ultimately end up at 0. Okay, so this is the diagram for null. Okay. Now, U is not invertible, right? It has a row that is 0, or if you want, its columns are not linearly independent. The third column certainly is a linear combination of the first 2. But L is invertible, Okay? Which means that the only vector that ends up here has to be 0 here. Any other vector would go somewhere else. So now the question is, which vectors in the original input space does u send to u? Does u send to 0? Okay? So if I take my matrix, I really want to solve this equation. Okay, let's cash this out and write it in transformation in equation notation. So I can say that x equals minus 5 times z, y equals minus 3 times z, and z is free. I don't have any information about z. So this is the solution of this equation, and based on this understanding, that means that any solution here really is telling me the null space of u, and hence the null space of A. Okay? So how can I further write this down? I can say, for instance, that any vector then any solution is of the form xyz. Plugging in the expressions, I get minus 5z, minus 3z, and z. Taking out z, which is the constant, it's a scalar, z times minus 5, minus 3, 1. That is to say, the vectors in the input space that u sends to 0 really are only the vectors that are proportional to minus 5, minus 3, 1. That is to say, they have to be in the span of this vector. Okay? So this means that in our picture, if I were to look at all these solutions, all those vectors that are sent to 0 under u and hence under A, they constitute a line. And I can draw that line to visualize how that null space looks like really. So this is the argumentation for the null space. So let's try to draw this. So x is minus 5. Okay. Goes into the back, I guess. Oh, let me do here. This is minus x, okay? 1, 2, 3, 4, 5. That's minus 5. Y is, this is minus y. I just changed my perspective. 1, 2, 3, so that I can draw it better. And then this is z, is 1. So it's something like this. Through this point, there passes a unique line, and that is the null space. Okay? So you see, you started with 3 dimensions, but this particular one-dimensional subspace in the input space is collapsed under U, and hence collapsed under A. And that is what the null space of A really is telling you. All those inputs that are ultimately sent to 0. Okay? Questions about this? Now note that if instead of trying to come up with this particular vector, I was just worried about the dimension of this, so in this case it's 1 because it's a line, I could do the following. I could look at U, the reduced echelon form, and I could say that, oh, I have two pivot columns, right? The first column is a pivot column. The second column is a pivot column. So pivot columns are where you have a staircase, you have a step in your staircase. The third one isn't, okay? The fact that you have one non-pivot column corresponds to the fact that you have a one-dimensional space that is the null space of A, okay? So let me write it here. So I'm going to call, how should I do this? Dimension of null space is the same thing as the number of non-pivot columns of A. Okay? Yes?
Sorry, what's the null line again? Like, where does that come from?
Oh, I just drew this.
Okay. That is the. Okay.
So recall, so what is the definition of the null space? The null space is really all those inputs that ultimately under A are mapped to 0. Okay. So this is the idea. I separated the back end and the front end. The front end is an invertible map, which means that, so if L goes from here to there, L inverse goes from here to there. So the only things that end up being here has to be 0 in the middle part. So now the question is, it really reduces to which vectors here does U send to 0? And in terms of a linear system, it is really the space of solutions of that linear system. I just used U times some input vector equals 0, and I solved it. I mean, it was already in reduced echelon form, so it wasn't that much to solve, but still. Okay, so let's. So for instance, if I were to take this vector and apply A to it, 1, minus 3, minus 4, minus 4, 6, minus 2, and then minus 3, 7, 6. I want this to end up at 0, 0, 0. Okay, so let's check this out. So 1 times minus 5, so this is a column vector, of course. Minus 5 plus 9 minus 4, 0. 20 minus 18 minus 2, 0. That's a 3. 15 minus 21 plus 6, 0. Okay. So this vector is in the null space of this transformation. But not only this vector, of course. Any constant multiple 2 has to be in the null space. And I'm saying this calculation really shows you that there is no other vectors that does this. Any other vector that A ultimately transforms to 0 has to be a constant multiple of this in this particular case. Geometrically, this just means that the null space is one-dimensional. And it is a line spanned by this particular vector. Okay. Any other questions? Yes?
I guess it's probably always the case that U is not invertible because U is the reduced echelon form of A.
Uh-huh.
And L is just all of those transformations, and so generally L should be invertible and U should not.
Well, okay, that's a good point. But certainly, this is a valid reduced echelon form. Okay? That is to say, if you were to start with A invertible, your reduced echelon form 2 would be invertible. So that is not quite always true. But if it were the case that U is invertible, then you would have said that, oh, the null space is really 0. It only consists of the 0 vector.
Because if it's invertible and you can go to 0, to get to 0, you basically probably have to multiply by 0? Is that?
Yeah, exactly. Yeah, so if this were invertible, I could just go back using U inverse, like I did here. But it's not invertible. It's collapsing one dimension. Okay? Good. So now let's do the same thing with the column space. We figured out all those vectors in the input space that ultimately end up being at 0 to compute the null space. For the column space, you do something similar, but it's sort of backwards. Let me draw the same diagram. So now this is the column space. Now last time we discussed how the column space is really the span of all columns of A. Okay? And in other words, it's really all those vectors in the output that come from somewhere here. Okay? So for the null space, we looked at all those vectors in the original input space that ultimately end up at 0. For the column space, I'm taking any input vector whatsoever, and I keep pushing forward and see where I can end up at. Okay? So if I were to take a vector here, and if I were to send it to this space using U, this really is a linear combination of the columns of U. Okay? Okay, I'm going to keep that and write it here. We don't need this. Right, so if I need to figure out where an arbitrary input ultimately ends up at, first I can apply U to it, and then L to it. So first, let's look at this. Column space of U is the span of columns of U. And you see, this is where this reduced echelon form really starts to shine, because if I were to look at my original matrix, I have no idea. It's not apparent whatsoever. But if I were to look at the reduced echelon form, I can immediately see that the first two vectors, the first two columns are linearly independent. One is in the x direction, the other one is in the y direction. And then the third column is certainly a linear combination of these two. Okay? So the span of columns of U, which I can write like this if I want it, using the notation, and then 530. This is this span. But then recall, this is redundant. In order to go to places in the span, all I need is to be able to move in the x direction and in the y direction. This is also letting me move, but really I don't need this. This is redundant. So I can just discard it so that I have now two vectors. The span will be the same. That's what it means for a vector to be redundant. Okay? What is this? This means that, so this is the xy plane. So this means that no matter what input I use, once I apply this first transformation, it's going to end up at somewhere here. So this is the column space of U. What is important, of course, is that its dimension is 2. Okay? It is a plane. It has 2 dimensions. And when I apply L to this, what's really going to happen is that this is going to be configured to be in a different position. But it's still going to be a plane. How can I figure out where this is sent to under L? Any ideas?
Could you do like xy times L to see where the xy kind of end up?
Yeah, I mean, exactly. Yeah. So I can say that this xy plane, so there's the 1, 0, 0 vector, and then 0, 1, 0 vector. And certainly I can apply L and get somewhere else. So drawing this is going to be more painful, probably. I'm going to erase this, but before I erase it, let me just note that now I have 2 pivot columns and 1 non-pivot column. I told you that the dimension of the null space is the number of non-pivot columns. The dimension of the column space is the number of pivot columns. It's a plane, and it's 2-dimensional. Okay? This is about, so the pivot columns are about the column space. Non-pivot columns are about the null space. I'm going to write this down explicitly in a second once we're done with this. So, of course, I erased L, but I have it written down somewhere. So L was this. And to figure out where L sends any vector here, which came from this space, to, well, all I need to do is to plug in x, y, 0 and apply L to it. X, y, 0. So this means that this is going to zero out the third column, and really all I'm going to get is a linear combination of the first 2 columns of L. So x, 1 minus 4 minus 3 plus y minus 3, 6, 7. So span of 1 minus 4 minus, so this is in the span. This, comma, minus 3, 6, 7. And this now is the column space of A. Okay? So now drawing this is somewhat harder. In fact, I'm not going to even try drawing this. Okay? It goes to a plane. It goes to some other plane. What I can do is this. I can change my coordinates, of course. So let's say that this really is 1 minus 4 minus 3 in 3-dimensional space. And the other one is minus 3, 6, 7. Whereas here it was 1, 0, 0, and then 0, 1, 0. And then here too. And then if I use these vectors, now this is the column space of A. Okay, yeah.
So getting the column space of L given the column space of U gives us the column. So I guess xy0 is the column space of U, correct?
Exactly.
And then that times the column space of L gives us the column space of A.
Exactly. Yes. So, but now, note that you don't really need to go through all this stuff. If you were to perhaps look back at your notes, you're going to realize that this really is the first column of A, and this is the second column of A. I did all this stuff, but we ended up with the same thing. It was all in front of our eyes. So, first column of A, and this is the second column of A. Now, how did I figure out that I should be using first and second columns of A? Really, I had to, again, go to the reduced echelon form. And in the reduced echelon form, the first and the second columns were the pivot columns. Okay? And if you know which columns are the pivot columns, you can go back to your original matrix, and the corresponding columns are going to span the column space. Any questions about this? So now let's tighten the calculations. Oh, let me mention one more phrase. I'm going to use the word, before that, let me just do this. So the dimension of the null space, we said, is the number of non-pivot columns of A, and conversely, or vice versa, dimension of the column space of A is the number of pivot columns of A. Because these are so important, these two things, they have specific names. The dimension of the column space of A is called the rank of A. Not to be mistaken by PageRank or with PageRank. It's a different thing. This is called rank of the matrix. It's a number. And this is called the nullity of the matrix. So, nullity of A. Okay? Well, if I have this many pivot columns and then that many non-pivot columns, I don't know what those numbers are, but certainly they should add up to the number of total columns of A. This is the content of the fundamental theorem of linear algebra, and I'm writing it here. Of linear algebra. The rank of a matrix plus the nullity of a matrix equals the number of total columns, which is equal to the dimension of the inputs. So rank plus nullity equals dimension of input. Okay? Any questions about this? We're going to spend more time on this theorem later. This is not quite the whole statement. It's just one part of it. But it's still a good place to start. So let's do another example, okay? Now faster. Here's another example. Let's say that I have this matrix. So A is equal to minus 3, 6, minus 1, 1, minus 7. 1, minus 2, 2, 3, 1, 2, minus 4, 5, 8, minus 4. I'm not going to spend too much time on reducing. In fact, I'm going to spend no time whatsoever. But this is a 3 by 1, 2, 3, 4, 5 bit matrix, which means that I can think of it as a transformation from 5 dimensions to 3 dimensions, right? Because the number of columns is the number of input dimension, and number of rows is the number of output dimension. So, and let's say that I want to figure out the column space and the row space, null space of A. First things first, again, I need to row reduce. Let me just say that A row reduces to this. 1, minus 2, 0, minus 1, 3. 0, 0, 1, 2, minus 2, 0, 0, 0, 0, 0. Okay? This is indeed reduced echelon. Let me ask, what is the dimension of the column space of A? 2, right? Because you have 2 steps. What is the dimension of the null space of A? 3. Exactly, it's the rest. You see, whenever you don't have a step, those contribute to the null space. Whenever you do have a step, they contribute to the column space. So let me just write it like this. Rank of A, dimension of the column space, equals 2. Nullity of A is the rest. It's the dimension of the null space is 3. They add up to 5. This is the number of columns. It's also the number of inputs, and it's also the number of unknowns if you started with a linear system. So 5, number of columns, dimension of input, which is equal to the number of unknowns. These are all the same thing. So now you see, you can think of it like this. You start with 5 dimensions. Applying A kills 3 dimensions. You're left with 2 dimensions. Even though it seems like initially you have 3-dimensional outputs. You don't quite get the whole thing. Okay? Somehow, along the way, you're killing too many dimensions when you're applying A. Okay? That's how you should think about this. So this is the first step. You see, the rank and nullity is just telling you the dimension. It's a number. Now, if you really want to compute the column space and the null space, that is to say, if you want to figure out vectors that span these spaces, you need to do some more calculations, okay? Let's start with the column space. You look at the pivot columns. So it is the first and the third. Now it is important which ones are the pivot columns. You go back to your original matrix. Your column space are going to be spanned by these 2 vectors. Okay? So the column space, let me write it like this. Pivot columns 1 and 3. So the column space of A is spanned by the first column and the third column. And further, I know that, so 1, 0, 0 and 0, 1, 0 certainly are linearly independent. The same relation holds when you go back to the original matrix. That is to say, this set really is optimal. You cannot get rid of one of these without dropping the dimensions. Okay? So you have 2 dimensions in the column space, and you get a set of 2 vectors that span the whole space. Okay? This is what is referred to by the word basis. And this and -1 to 5 are linearly independent. Whenever, for any subspace whatsoever, it doesn't need to be the null space or the column space, for any subspace, if you can find a set of vectors that are both spanning the whole space and are linearly independent, that is called a basis. Okay, that's an important definition. So important that I'm writing definition here. For S a subspace of Rn, a set of vectors in S is called a basis of S if it is linearly independent. It is linearly independent and it spans S. Okay? So I could say that the pivot columns of A is a basis for the column space of A. It's a spanning set of vectors that are non-redundant. Okay? So this is the first stage. For the column space, it's slightly easier, or maybe it's slightly harder compared to the column space. You do need to do some calculations. You look at the, well, let's just look at this. I look at the reduced echelon form, turn it back into a linear system, and I can write it like this. So x1 equals 2 x2 plus x4 minus x5. x2 equals minus 2 x4 plus 2 x5. x2, x4, and x5 are free. So based on this, I can write a typical vector.
Isn't it x3 is equal to -2x4?
That's true. Thank you. This is coming from, right, reading the second row over there. So I can write it like this. So x1, x2, x3, x4, x5 is really x2 times a vector plus x4 times a vector plus x5 times a vector. And then you read out these entries. This is just this. 2, 1, minus 3. x2 is just x2, 0, 0. x3 is 0 here, minus 2 here, 2 here. x4 is 0, 1, 0. x5 is 0, 0, 1. So now that you have this, you say that the null space is spanned by these three vectors. And note that they are linearly independent. I can immediately say this because only the first vector allows me to move in the second direction. Only the second vector allows me to move in the fourth direction. And only the third vector is allowing me to move in the fifth direction. So 2, 1, 0, 0, 0. 1, 0, minus 2, 1, 0. And minus 3, 0, 2, 0, 1 is a basis for null of A. It's three-dimensional. I get to display three vectors that span the subspace.
And you knew those ones were free because that's where they don't have pivot points?
Exactly. Yes. Number of free variables is the number of non-pivot columns. Okay?
Where did the numbers in the vectors come from?
Well, okay, I can write it like this, right? So x1, so I start with this. Replace x1 by this expression. x2 I cannot do anything, but x3 I can replace by this expression and so on. Now I have 5 entries, each of which is in terms of x2, x4, and x5. Then I can split those and pull out these constants. If you don't believe me, you can just consolidate this right-hand side expression and get this. Okay, so for instance, this first one gives me 2x2 in the first row, and then plus x4 minus 3x5, which is equal to x1. Okay. Yeah. So I'm reading this row by row. Now the reason why I went through that more complicated geometric discussion earlier is to point out this procedure. And there's one thing that you should keep in mind, which is that the null space of the reduced echelon form of a matrix is the same thing as the null space of the matrix itself. Whereas the column space of the reduced echelon form is not the same thing as the column space of A. Okay? You need to apply some transformation that corresponds to this row operations to get the correct configuration. The dimensions are going to be the same. So this has rank 2, and my matrix 2, original matrix 2, has rank 2. But how they are positioned in three-dimensional space is going to be wrong. It's going to be different. Okay? Right? So because the column space of this is just the xy plane in the three-dimensional space. Whereas the column space of A is certainly not the xy plane. You have some motion in the z direction. Their dimensions match, but not quite how they are configured in 3 dimensions. Okay? So now we covered pretty much everything. On Monday and Tuesday, we're going to discuss affine transformations in the context of computer graphics a little bit. But this is sort of the main thing that you should really focus on. Start with a linear system. Go all the way to here. Column space, null space, and everything. Okay? This is the content for the first midterm. Any questions about this? Yes?
So your column space of A is going to be the vectors over there that are linearly independent?
Yes. Well, not quite the vectors, but their span.
Okay. And then these ones, is this one also a span, or is this
Yes, yes.
free?
Yes, this is also the, so I just wrote it like this. This is, So these three vectors does span the null space of A, but further, they're also linearly independent. That is to say, they are a basis.
Okay, so you could say those ones over there are the basis.
Exactly.
Okay.
These two is a basis for the column space, and these three constitute a basis for the null space, which with matches because 3 is the output. You see, these are in the output, and null space is supposed to be in the input space, and these are 5-dimensional vectors. Always count the dimensions of things as a heuristic, okay? And now you have two more numbers to keep in mind, rank and nullity. And they have to add up to the dimension of the input.
And that's why those ones are 5 and those ones are 3.
Exactly. So purely based on the fact that I had two vectors that is a basis for my column space, I knew that I was going to have 3 vectors for the null space. Because the number here, which is 3, right, that's the nullity, has to add up together with the number of these two, which is 2, to 5 number of columns. Okay? Good. I think it's a good place to stop. I know this is somewhat rough, but once you start doing exercises, I think it's going to make more sense. Thank you. Have a nice weekend. I'll see you on Monday.